Today is the third lecture for an AC circuit. Now today we'll discuss about the power dissipation which we have left in the last lecture. Power dissipation. Okay. Now what we know is that we have applied voltage Vt is equal to V sine V naught sine omega t. Okay, it is applied voltage in a circuit, and the corresponding current we have assumed to be I naught sine omega t minus theta. So the instantaneous power can be given by Pt is equal to Vt into It. That is very much obvious. So this could be written as V naught I naught sine omega t into sine omega t minus theta. So or it could be written like V naught I naught by 2. Okay, this could be divided by 2 and multiplied by 2. So that will give you cos theta minus cos 2 omega t minus theta. Okay, using the basic trigonometric rule. So this will be your equation number 1. Now the average power over a cycle, this could be given by, okay, that is the average power 0 to t pt dt, okay, divided by dt from 0 to t. So this will be your equation. Now substituting this value pt over here, okay, we get the relation, which is the average value rather. So p average. Okay, now one thing we have to remember is that the integral okay, of cos 2 omega t minus theta will be 0 over a complete cycle. So ultimately you'll get p average equal to, okay, as after calculating this thing you'll get V naught I naught by 2 into cos theta. So now from here you can write it like this: V naught by root 2 I naught by root 2 into cos theta. So this is your equation number 3. Now the term here cos theta is known as power factor. Okay, now for cos theta, we know that cos theta is less than or equal to 1. Okay, so the power dissipation in an AC circuit is less than the product of, this is Vrms and Irms. So it is less than the product of Vrms and Irms. Vrms into Irms, except when cos theta equal to 1. So for cos theta equal to 1, okay, the current and the voltage are in phase. Okay, V and I are in phase. Okay, and we have resonance. So we have resonance. Okay, so resonance, okay, for unity power factor, your resonance are synonymous. Okay, so the product of the RMS, Vrms and Irms, it is known as apparent power. Okay, so product of Vrms into Irms is known as apparent power. This is known as apparent power. And simply what we have done earlier, the PT, this one, the first equation, this is the real power. So the real power, ultimately you get the real power. So listen to something like real power into apparent power, okay, into power factor. So this is the ultimate relation. We have this substitute over here. This is what we are telling you. This is the real power, this is the apparent power into the power factor. This has to be there in the mind. Now we can show this thing, the variation of Vt, It and Pt with respect to omega t in a figure. So the instantaneous power Pt is given by the product of Vt into Ip. So we'll just draw over here a diagram. So a curve can be drawn where we can just show the variation Pt, Vt and It with respect to omega t. Okay, and here we'll show Pt, It and Vt. Okay, with respect to omega t. What we can show is that if you talk about Vt, let's start from here. As current slightly lags behind, so depending upon the value of theta, so this will be, the current. This is Vt, this is It. So it will be something like this, and then we have the power, rather Pt. So it will start. Okay, so it will start from here, it will go like this. So this will be your power. Okay, so it will come down. So this is your Pt. Now we'll talk about the how to analyze this one. What we can say is that the instantaneous power is given by the product of Vt and It, and is positive for the values of t for which Vt and It will have the same sign, that is both Vt and It. If both are positive, then Pt will be positive. Okay, and the positive value of Pt implies that the source of supply is delivering energy. So what we can, positive Pt implies that the source of supply is delivering, okay, energy to the circuit, and when Vt and It have opposite sign, it implies that the source supply is receiving energy from the circuit. So negative opposite sign implies that it is receiving energy from the circuit. Okay. Now when theta is 90 degree, no, this is a special case. When theta is equal to 90 degree, that is when the current and the voltage are in quadrature, the positive and negative area under the Pt curves are equal. Okay, so in this case, no net energy is delivered to the circuit, and the average power being 0. So P average will be Vrms I RMS cos theta. So for theta equal to 90, this will be 0. This case occurs when the circuit is purely inductive or purely capacitive. Okay, for purely inductive or capacitive circuit. Okay, and the current is called wattless. The current in this situation is called wattless. Now, as far as parallel RLC circuit is concerned, there are so many things to discuss in parallel LRC circuit. Okay, now the thing is that we need to understand that it is not possible to summarize everything in this particular lecture. So we'll just do a part of it. So regarding parallel AC circuit, just draw. Say this is an inductance. Okay, this is your capacitance, this is the resistance. These are all connected in parallel. Okay, and this is the source. So this will be E equal to E naught sine omega t. Here there is the current IR instantaneous, IC instantaneous, and IL. So if this is I, so we'll have I is equal to IL plus IC plus IR. Now how to find out the value of this current actually? So what we'll do is that if we'll talk about IR, so we'll talk about IR, we'll write E is not sine omega t by R, which is there only. Now it will talk about, so this is a question number 1 or 2. Then we'll have IC. So for IC we'll write dq by dt. In the place of q we'll write q is equal to ce by dt. So d c e naught sine omega t by dt, that will be given by c e naught. After differentiation we'll have c e naught omega cos omega t. So this is your IC, and as far as IL is concerned, we'll have for IL we know that VL is equal to L di by dt. Okay, that we know. So DIL by dt. So DIL by dt will be equal to E naught sine omega t, okay, by L. What we have done over here is that we have just mentioned over here is that di by dt, IL will take d small I L by dt equal to VL by L, or so we'll just write E naught sine omega t by L, and then we'll just integrate this one. Okay, after integration, DIL is equal to E naught sine omega t dt by L. Integrate this one, we'll get IL is equal to minus A naught by omega L cos omega t. So these are the three values, IL, VL and IR. Now substituting this value of IL, IR and IV, IR, IL and IC in equation 1, we'll have I is equal to E naught sine omega t by R plus it was C omega E naught cos omega t minus E naught by L omega cos omega t. Properly taking out the common term, we'll have sine omega t by R plus C omega minus 1 by omega L into cos omega t. Okay. So ultimately what we do is that we'll just do a bit of substitute something like this. 1 by R is equal to, we'll write over here A cos theta, and C omega minus 1 by omega L as A sin theta. Okay, and substituting this equation, we'll get I is equal to E naught A sin omega t cos theta plus A cos omega t sin theta. So we'll have E naught into A sin omega t plus theta. So in the place of this, we'll write I is equal to I naught sin omega t plus theta, where this one is the peak current. Okay, and again we'll see this one, we'll divide this second one by the first one, we'll get tan theta equal to, okay, we'll write R C omega minus 1 by omega L. This is C omega. So dividing this one, okay, this 2, we'll get the relation tan theta. Now this is what we have done today related to the parallel LRC circuit. We'll discuss resonance in parallel LRC circuit in detail in the next lecture. Until then, thank you.